Welcome to the video lecture on biometrics. We're going to be looking at essentially two different aspects of biometrics this afternoon. Essentially, what we want to look at is biometrics in the form of identifying human beings to computing devices via something that they are, e.g. a fingerprint or a retinal scan or something like that, an iris scan, or possibly the ability to use handwriting. We'll be looking at something we call identity-based crypto systems, which are cryptographic systems based on something you have or something that you are, which might not necessarily be a fingerprint or an iris scan. Could be an address or an email address or a phone number, something like that. So a couple of little videos we're going to look at, and let's get started. Okay, so let's talk about fingerprints. The lecture today is going to be on biometrics. I'm not convinced it's going to be one of the longest lectures I've ever done, but it'll certainly, I believe, be eye-opening and give you a little bit of insight into the whole topic of biometrics. We're going to start by looking at fingerprints, as I just mentioned. The whole objective of using fingerprints or some other biometric feature is to authenticate a human being to a machine. Now, there have been numerous schemes that have been considered over the years, fingerprints being the number one biggest or most widely spread use of biometrics. Also, such techniques as iris scanning, handwriting is another method. Generally, we would use something such as a fingerprint in combination with, for example, a passcode. A lot of the secure doorways on campus, for example, will use a fingerprint scanner plus a passcode, or a fingerprint scanner plus a token. The token being some kind of an RFID identification device. Fingerprints are very good for identification because, as we know from popular science, there are no two that are the same. We have essentially three primary patterns that we see in fingerprints. We see what we call arches, which compose about 5% of all fingerprints. Loops, which are about 65% of all fingerprints, and whorls compose approximately 30% of all fingerprints that we find in the world. Now, when we actually examine fingerprints, we find that those are very general, they are overall patterns, and that those patterns can be made up of other patterns or sub-patterns. So we have things that we call line types, and we'll look at that here. A number of different line types. We have arched lines, and fingerprints made up primarily of arches are classified as arch prints. Bifurcation, this is where the two different lines converge or diverge. In other words, they come together or come apart, and you can see that here in this little diagram. Oval-shaped ellipses, often we will find these at the middle or in the center of a whorl pattern. If you look at this pattern, you'll see this little line. We call this an island, And that is just a solitary line, stands generally in the middle of two other lines. And the issue here is, or the thing that separates this from a bifurcation, I should say, is that this small line does not intersect with any other lines, which makes it an island. Loops. This is a line that obviously loops around, and a rod is a straight line, often found in the middle or in the center of a fingerprint pattern. We have spirals. We have sweat glands. And we call this a tented arch because it rises very quickly and it looks like a little tent pattern, a little pup tent, or maybe a teepee. And those particular patterns are what we generally refer to. Oops. Let's bring some things together here. We also have patterns that we call minutia, and minutia are really combinations of these different line types and the small patterns or the small sub patterns that we see occurring within the general fingerprint. So if we look at the example on the screen, you'll see things. For example, we see a ridge ending. We see bifurcation. We have an enclosure. Another ridge ending, another enclosure, another bifurcation. We call this a ridge dot. And these are the tiny sub patterns that actually make up the fingerprint. The job of the fingerprint scanner obviously is to be able to read these patterns and make some kind of sense out of them. The fingerprint scanner itself is generally going to use an infrared beam or an infrared light, and it generally will penetrate, depending on the scanner it is, will penetrate into the skin and maybe go 2, 3, or 4 layers deep. Now there are some very, very high security scanners that encompass other features, and we should probably talk about that. So one of the features is, of course, liveness tests. So if I need to, for example, if I was a bad guy and I wanted to defeat a fingerprint scanner, one way that I might be able to do it is to actually cut off the finger of somebody who had access and use their finger. The way that we would actually prevent someone from being able to do that is to use liveness tests, looking for blood flow, that sort of thing. Other methods that are used is, for example, to create a false fingerprint. There's different techniques for doing this. The technique that's actually hit the news most recently has to do with the use of a false fingerprint made using liquid latex, where a person's fingerprint is lifted off of an object using the traditional techniques that, for example, a police forensics examiner would use. That is dusting for the fingerprint, using tape, lifting it, putting it onto a paper, then scanning it into a computer and cleaning it up. It can then be printed onto a transparency using super heavy duty toner. In other words, a super thick application of toner. The other method, and then painted over with liquid latex, and the liquid latex is allowed to dry. It's then peeled off, cleaned up, and if the perpetrator is lucky, it can be moistened maybe by just sort of breathing on it, and then applied to a fingerprint scanner. Now you'll find various examples of this if you, for example, look at the new iPhone 5S, and there are videos on YouTube that show that fingerprint scanner being defeated using that technique. At first I thought it was somewhat interesting that that phone was defeated using a technique that I've actually been talking about in classes for years and years. And I thought that was interesting, and I really had to sit back and think about it. And then when at the end of the day, what I realized is that the phone is simply that, it's a telephone. It's not protecting nuclear secrets. So why would we get particularly surprised? It's a fingerprint scanner, and it's designed to provide security in an easy-to-use fashion for people who would otherwise not actually use the security feature. And now, having said that, I wanted to look at a short video. And yes, it is a video for the iPhone 5S. So let's bring that screen in. And make it full screen. And play.
Extends to how we protect all of the important information that you actually carry with you on your iPhone. It's what led us to create Touch ID.
Your fingerprint is one of the best passwords in the world. It's always with you, and no two are exactly alike. So it made perfect sense to create a simple, seamless way to use it as a password. With just a touch of your home button, the Touch ID sensor quickly reads your fingerprint and automatically unlocks your phone. You can even use it to authorize purchases through our stores for music, movies, TV shows, apps, and books. Setting up Touch ID to recognize your fingerprint is easy, and every time you use it, it gets better at reading your print. It can read multiple fingerprints and read them in any orientation. The technology within Touch ID is some of the most advanced hardware and software we put in any device. The button itself is made from sapphire crystal, one of the clearest, hardest materials available. This protects the sensor and acts as a lens to precisely focus it on your finger. The steel ring surrounding the button detects your finger and tells Touch ID to start reading your print. The sensor uses advanced capacitive touch to take, in essence, a high-resolution image of your fingerprint from the subepidermal layers of your skin. It then intelligently analyzes this information with a remarkable degree of detail and precision. It categorizes your print by one of three basic types: arch, loop, or whorl. It maps individual details in the ridges that are smaller than the human eye can see, and even inspects minor variations in ridge direction caused by pores and edge structures. Touch ID uses all this to provide the most accurate match and a very high level of security. All fingerprint information is encrypted and stored inside the secure enclave in our new A7 chip. Here, it is locked away from everything else, accessible only by the Touch ID sensor. It's never available to other software, and it's never stored on Apple servers or backed up to iCloud.
Touch ID defines the next step of how you use your iPhone, making something as...
Okay, so there's your Apple commercial in my lecture. Okay. So I think that video is very, very good. I used it specifically because it reinforces some of what I've just been talking about. It provides us with the idea of using biometrics provides us with some reasonable level of security. It may not be a level of security that we're particularly going to use to protect nuclear secrets or atomic bombs or that type of thing, although it is used for those purposes. But it is reasonable. As we've noticed, as we've discussed in earlier classes, one of the reasons people don't use security is because it simply is a pain to use. So let's move on and look at another form of biometric that is a little bit kind of interesting, and that is the use of signatures. Signatures have been used to protect documents and to protect, for example, things like checks for quite some period of time, years and years, possibly hundreds of years. And the art, and I would call it an art, of defeating that is just as old, where people would forge other people's fingerprints. The concept of using handwritten signatures with biometrics is that we can hopefully create something with a reasonable acceptance level, and this also applies to fingerprints, where the individual can verify that it is indeed them using their signature, and that it's more difficult for a forger to actually defeat the system. Now, handwritten signatures traditionally are done in a static mode. In other words, I write you a check, you take the check to the bank, the teller at the bank looks at the check, looks at a known copy of my signature and says, it looks sort of the same, and they cash the check for you. In an electronic world, we actually have sensors where we can actually validate the signature live. And this is a very interesting science, and it is still experimental. Of course, there are also machines that work very similar to fingerprint scanners. They can also validate your signature by looking at it in static mode. Things that we look at are things such as the maximum distance between the highest and lowest point in the signature. How long is that signature on paper? What is the standard deviation of the change in X or the change in Y? The initial direction of the pen. We can also measure things such as the pen ups, the pen downs, the speed of the pen. And these are things that are very, very difficult for a forger to reproduce. Now, a forger can fairly easily learn to reproduce a signature that looks the same as something they've been given to replicate. On the other hand, in order for the forger to defeat the handwriting scanner, they have to be able to reproduce the live signature. Now, there have been experiments done where a skilled forger has been allowed to witness the original signature being made live, and then work on being able to reproduce that. It is a long and labor-intensive process. The main reason being that there are many factors that are studied by this technology. So the forward velocity of the pen. What is the maximum forward velocity? How fast is it moving across the paper at its highest speed? Whereabouts in the signature does that happen? At what point is the first time when the speed of the pen becomes 0? What about the average speed with respect to X and Y? In other words, what's the maximum speed at an angle? Average writing speed, number of times the pen lifts on and off the paper. What is the second time that the pen goes down on the paper? What direction is the pen moving at the first time it goes down, or what is the direction it moves at the first time the pen goes up? How many dots? In other words, how many I's are recorded, things like that. How many periods? And also we can look at the times when the pen is moving backwards over X and Y axis, and the total time that it's moving forward on X and Y axis. So as you can see, there's a fair bit of complication with regard to the actual speed of the pen, or actually measuring the pen and validating the fingerprint, or the handwritten signature. I also have a page here while we're talking about biometrics. I also have a page, and this is from Bruce Sneyer's weblog, and I'm going to see if I can make the text a little bigger here, and I'll read this to you. Fun with fingerprint readers. Tsumoto Matsumoto, a Japanese cryptographer, recently decided to look at biometric fingerprint devices. These are security systems that attempt to identify people based on their fingerprint. For years, the companies selling these devices have claimed that they are very secure, and that it is almost impossible to fool them into accepting a fake finger as genuine. Matsumoto, along with his students at the Yokohama National University, showed that they can be reliably fooled with a little ingenuity and $10 worth of household supplies. Matsumoto uses gelatin, the stuff that gummy bears are made out of. First, he takes a live finger and makes the plastic mold. He uses a free molding plastic used to make plastic molds and is sold at hobby shops. Then he pours liquid gelatin into the mold and lets it harden. The gelatin comes in solid sheets and is used to make jellied meats, soups, and candies, and is sold in grocery stores. This gelatin fake finger fools fingerprint scanners about 80% of the time. His more interesting experiment involves latent fingerprints. He takes a fingerprint left on a piece of glass, enhances it with a cyacrylate adhesive, and then photographs it with a digital camera. Using Photoshop, he improves the contrast and prints the fingerprint onto a print transparency sheet. He then takes a photosensitive printed circuit board and uses the fingerprint transparency to etch the fingerprint onto the copper, making it three-dimensional. Finally, he makes a gelatin finger using the print on the PCB. This also fools fingerprint detectors about 80% of the times. Gummy bears can even fool sensors being watched by guards. Simply form the clear gelatin finger over your own. This lets you hide it as you press your own finger onto the sensor. After it lets you in, eat the evidence. And it goes on that Matsumoto tried these attacks against 11 commercially available fingerprint biometric systems and was able to reliably fool all of them. The results are enough to scrap the systems completely and to send the various fingerprint biometric companies packing. Impressive is an understatement. There's both a specific and general morale to take away from this result. Matsumoto is not a professional fake finger scientist. He's a mathematician. He didn't use expensive equipment or a specialized laboratory. He used $10 worth of ingredients you can buy and whipped up his gummy fingers in the equivalent of a home kitchen. And he defeated 11 different commercial fingerprint readers with both optical and capacitive sensors, and some with live finger detection features. Moistening the gummy finger helps defeat sensors that measure moisture or electrical resistance. It takes some practice to get it right. If he could do this, then any semi-professional could almost certainly do much more. So be very careful before believing claims from security companies. All the fingerprint companies have claimed for years that this kind of thing is impossible. when they read Matsumoto's results, they're going to claim that they don't really work, or that they don't apply to them, or that they've fixed the problem. Think twice before believing them. Okay. And so, just some interesting takes on this whole concept of biometric security. And I'm sure you're going to have your own ideas with respect to biometric security. So that's a fairly brief introductory look at biometrics. Finding it interesting here, lecturing to a video screen instead of lecturing to my class. I almost think I should have a still picture of you folks on the screen, so I feel like I'm standing in front of the classroom, and I know what other instructors I know who have had to do recorded lectures, I know how they feel now, because they've all said it's sort of an eerie feeling and somewhat disconcerting to sit and talk to myself. So there's probably a few rough edges on my lecture still, and it will need a certain amount of video editing over the coming months. But in all, I want to summarize that biometrics is with us. It's here to stay. There are more and more companies that are going to be implementing biometric security. Apple has now released a cell phone with biometric security on it, and you can bet that other companies are going to be soon following suit. You realize that this is a game of catch up and keep up with these companies, and the more fancy features they can sell, the better the more money they make. And if one company produces a fingerprint scanner, everybody wants to produce a fingerprint scanner. We talked about other forms of biometrics. For example, we've talked about handwriting, we've talked about fingerprints. I mentioned iris scanners. Iris scanners basically are scanners that look at the iris of the eye. And there are known instances where these types of scanners have been fooled simply by holding up a picture of somebody's eye. And then, of course, there's all the science fiction type defeats that we've seen. For example, James Bond movie where somebody creates a false eye and puts it in somebody's eye, or they do cosmetic surgery to make the irises the same, and all that type of thing, which is at this time science fiction. But as technology moves forward, I actually can see where those types of biometric exploits will be possible. So anyways, I hope you've enjoyed this. I've been having fun putting it together. Please forgive some of the rough edges on this video. Really, it's just based on the fact that I'm not in front of my classroom. So I will see you guys next week. I'm off to the security conference. There's lots of work for you to do. I've given you a set of presentation questions which you'll have to set up for next week, and I will post the groups and the question associated with that group to the Q Drive. So have a good week, and I will see you the following Tuesday. Bye for now.